All right. Thank you so much. Yeah, so as soon as Rizal told me I would have the opportunity to speak to you today, I knew exactly what I wanted to use that precious time for with a number of really, really esteemed AI leaders, which is that I wanted to try to lure you over to work on robotics. And so my strategy to do that is to convince you that now is the best time there has ever been as an AI expert to come and explore the space. And I think that there are a few things as compelling and as convincing as just trying to give you a quick introduction and see if I can get you excited about it, but also give you some like legitimate concrete jumping off points where you can actually pick this up and keep going with it. And so that's gonna be the nature of our time today. I'm gonna try to speed run an introduction to AI robotics and hopefully inspire some people to come work on this problem with all of us. So a bit of history on this. Full disclosure, it's not my first time trying to get my friends to come work in robotics with me. About 5 years ago, I started collaborating with some incredibly talented students in the Stanford Robotics Club, putting together both a robot embodiment and a course to try to do sort of a modern take on introduction to AI robotics. And we'll talk about both of those. We taught that course, the independent study course, for a couple years. In 2023, with the support of Professor Karen Liu and Dr. Jay Tan, that turned into part of the computer science curriculum. So we now teach CS123 twice a year. This is a hands-on introduction to AI-enabled robots. And my goal today is to borrow a bunch of material from that. I'll put all the QR codes at the end too if you're not like trying to be like super fast on the draw. But the important thing is everything from that class is open source. All the lectures, all the labs, all the code. And the class roughly breaks into 3 pieces. We sort of have like a big chunk in the beginning on full body control. I think that's like a super exciting and compelling part of robotics. If you start off learning on a Roomba, you are absolutely like missing out on the cool part. And so we just really believed that we wanted to actually provide students with the introduction to this. And I'm really excited to share with you as AI experts why like now is the time, while the approach has changed. And then same as the class, we have shorter sections on perception and action planning. So if you're watching your watch, don't worry. The first section is very long. The second 2 are considerably shorter. And we'll talk about how the robot sees and how the robot actually understands what actions it wants to take and how it actually sequences those actions. No class would be complete and no introduction would be complete without actually like having a robot. And so I'd like to introduce the robot that we'll be working with today. This is Pupper. Hey, Pupper. So Pupper's gonna follow me over here, and I just wanna talk for like 30 seconds about the goals of this robot. We wanted a robot that was approachable, but also safe to work with, something you could pick up on your desk, you could grab it was back drivable, it's friendly, but also really represented the state of the art in hardware design. And so if you actually look at these, I have a couple of Unitree robots at my house, if you tear them down, the motors and actuator in that robot look like the motors and actuators in this robot. And we'll talk about that right now. And actually, I intend to convince you of that as we talk a little about some algorithmic design. So I'm gonna leave Pupper over here for now. Maybe we can off the stage, and then he will come back to us in a couple videos. I have to immediately say thank you to 2 incredibly inspiring students, Nathan Cow and Gabriel Levine. They did a ton of design. You can actually see multiple iterations of Pupper over the years. You can see how much it changed, and that changed as we were chasing this sort of state of the art in like how you design these and how you make them easier to build, but also easier to do really, really cool AI on. And these folks are doing a startup, and so you can probably catch them in the lobby after this and see if you can make it into the seed. All right, so this is what students get. They show up, they get a box full of parts. Again, everything is fully open source, so if you leave and you're like, oh my gosh, I just have to build a robot, we finally got this down to kind of like laptop cost level. So this is sort of a high-end laptop. You can buy all these parts. They're all open source. Some are at Home Depot. Some you have to actually source the PCB directly. Some you can 3D print. There's also some really awesome folks out there who've actually kind of taken the torch and they will just sell you a kit. So I just think that's like really magical to watch the ecosystem jump in on these things. So without further ado, I want to get into the first of these 3 pieces. I want to actually start teaching you about AI robotics and kind of give you the excitement that we have. So we have to kind of start by what is the action space we're operating in here? So what does it mean to control this robot? This is a breakdown of what one of Pupper's legs looks like. It actually has 3 motors. So from the outside, it kind of looks like 2, but it's just like your arm. It has 1 degree of freedom, at the elbow, and then 2 degrees of freedom in the shoulder, and that kind of lets it do like wiggles and motions that are like a little bit more lively. So if you take that, multiply it across the rest of the robot, this is our task. We need to somehow output 12 motor positions at 50 hertz so that the robot looks clean. And somehow, if we get them all just right, the robot will be walking. And if we get them wrong in any small way, the robot will do something very different than walking. So I'd like to talk you through sort of the old way, and then we'll kind of build on top of that with the new way. The old way, we can start by just looking to nature and see if we can draw a little bit of inspiration from that. So it turns out some thoughtful people have actually cataloged the different ways that dogs and horses walk. And so you can see they have these different patterns. There's like, okay, there's a canter or there's a trot. The trot is the opposing feet, the canter are the front and the back. I'm very empirical, so I did validate this with my dog. So this is indeed a canter. They do this at high speed. And they do indeed trot. So this is the trot. You can see the oppositional feet coming down. Front, left, back, right, back, left. And that's gonna be our first assignment today. So what we're gonna do is we're gonna take the Pupper robot, we're gonna watch it in slow motion. So this is the first kind of gait stance that we're gonna get into. We're gonna have 2 feet up. Then we're gonna move forward. Oh, sorry about that, I'll play that video again. Jump back. And so what we wanna do basically is we're gonna write a high-level controller that coordinates the legs exactly this way. It's gonna be 2 up, all 4 down, 2 up, all 4 down. And the advantage of doing this is that it sort of makes it easier for us mathematically. Because now instead of just like 12 scary terms, well, now we've actually created some constraints. Like this first block and this third block kind of have to be synchronized. Same thing for the second and the fourth. That's still a lot of scary stuff though, because in a leg itself, we still figure out like how are all 3 of those motors coordinating their motion? Once again, we can kind of look to nature and try to sort of like, well, how do dogs walk? Let's look at that. In this case, we're gonna watch how Pupper walks. And we sort of look at what is the foot doing? Like, let's just make a trace of this foot in the world frame. And we can see, okay, this is actually less scary than it looks. It's just like an up and down sawtooth pattern. Like we can probably figure out how to do that. And if we put it in the reference frame of the robot, it becomes even less scary. Like, okay, we just need to make the feet move in triangles. And so if we make each foot move in a triangle, and then we actually coordinate the legs so they're in this oppositional gait pattern, if you put all the pieces together, hopefully it starts walking. This is where the students in the class have to do a bunch of somewhat painful trigonometry to figure out how to work backwards from each desired position into what those joint angles are. You don't have to do that. That's the great thing. It's all open source. You get the code. And so once you're all done, you now have those same 12 numbers, but now they're heavily constrained. You're like, okay, I got the gate controller on top. I've got inverse kinematics underneath that. I'm just trying to draw triangles. Like, I can do this. And I want to say thank you to a bunch of the TAs who spent so much time actually really tuning all these little gains and figuring this out to not just make it walk, but actually make it kind of walk cute. And so you saw the first version, there was no hope of that one walking cute. Then you saw the second version, that one kind of started to get a little bit cute. And an amazing team of researchers at Stanford on the medical side reached out and said, hey, would Pupper be interested in visiting the children's hospital? And we said, well, yeah, of course. And I'd like to show you, you'll see this gate we just talked about in action. It's sort of a chance to talk about the impact of some of this work. So thank you again to the Stanford research team. Let's share a little bit.
7-year-old Josh Summit misses walking his dogs during his time at the hospital. So Stanford Children's Health introduced him to the next best thing.
I kind of felt like I'm a little bit nervous to meet the dogs. But after I met them, they were very, very friendly.
A lot of robotics technologies get developed in a lab and never has any real impact on the world. But we can see immediately the impact of cheering these kids up.
Josh's mom has also seen a difference.
It's really sparked his curiosity. He can still be 7 and be excited and play.
So I find that just incredibly inspiring and exciting. And I just want to show, like, before we get into the cool AI part, I do want to give credit to some of the traditional robotics algorithms, just how much good you can do with those. And I want to show one more video. After we did this, one of the doctors in the hospital reached out and said, hey, I have a patient who recently had a heart transplant. And so she's actually not allowed to be around the therapy dogs because of being immunocompromised. Would Pupper be able to come and make a visit with her? And in particular, after heart transplants, it's very helpful to move around a little bit. And so we actually did bring Pupper out, and they've actually stayed in touch over time. And so I want to show a video of the new Pupper actually also walking. And this is something we're just really excited about, which is sort of helping kids get excited to move around. And so that was a really special day for all of us. And I want to say thank you to this whole team. This is the Dr. Pupper research team. They give us a ton of inspiration. They also give us a lot of homework. And so after we did this, they reached out and said, hey, we loved it. The kids loved it. We have a different thing we want to do, which is there's a moment where kids have to go into the operating room. And we'd love if Pupper could meet, it's a very high anxiety moment. We'd love if Pupper could meet the kids and walk them into the OR. But the kids are a little younger. Pupper's a little loud. It's a little stompy with that big trot gait you got going on. Could you give us a gait which is a little more tame? And maybe a gait that wouldn't trip if there was something small in the way. We said, okay, we could. Probably not heuristically though. And so this is when AI kind of starts to come into the picture. And so let's talk about the AI approach to walking now. You've heard reinforcement learning at a couple points today. Spoiler alert, that's the way. And so we started working with some amazing researchers at Google Deepmind, folks who kind of donated their time, and we started using a simulator to actually say, hey, can we just try letting Pupper run in sim? And we'll just give it a reward every time it kind of takes the commanded action. And every time it says something different than the commanded action, we'll just tell it not to do that as much. And we'll start updating the parameters of the neural network. And the short answer is this kind of actually works. But again, in the spirit of getting you stoked about robotics, I actually want to tell you like how to get it working. And the first part of how to get it working is to generate an insane amount of time steps. Reinforcement learning is sort of shockingly inefficient. We haven't solved that on this project. That seems to be the nature of the state of the art. And so what has changed though is physics simulators are getting amazing. And so simulators like MJX from Majoko can now do 200,000 time steps a second if you can get them on a strong card like an A100. At the same time, some of the AI services are getting better and better. Google Colab in particular will make A100 cards available for free to students. And so thank you to Ankush and JC who are here today. They actually built a Google Colab notebook where you'll get an A100 and you will train a full walking policy in under an hour. And so like we're super excited about that. It's like you can take a picture of this, you can go home and try it yourself. And you can actually try out these sort of tips and tricks to actually really get RL working in a real environment. And so to close out the section, I want to kind of talk about like the 3 little tricks you need to get RL working and sort of what has changed in robotics, partly get you excited about the space. And these are system identification, domain randomization, and reward shaping. And so these kind of, when we first started, like it looked so promising, it would kind of work in the simulator and then it wouldn't work on the robot, and like how do we handle this like sim to real gap? And this really has become the state of the art, and it's so fun to be able to teach this at an undergraduate level. And so system identification is just actually getting the information about the robot right. How torquey are those motors? How heavy are those arms? Where is the center of mass on this robot? So if you're like, I have a Sunday morning free and I want to try out reinforcement learning for full body control, I strongly recommend starting with a robot where somebody else has done the system identification. It will save you a lot of time and pain. We have done the system identification. So this is a real meaningful jumping off point. And so you can see a little bit of the work that the team put in into actually really kind of making that possible. Now, once you have the information about the robot roughly correct, you're still going to be a little bit wrong. Some of the time that center of mass is off a little bit. That might be variations between robots. That might just be the fact that you just didn't quite get it right. And this is where domain randomization comes into play. What you do is in every single time you spin up that simulator, you give it a slightly different center of mass, you give it a slightly different force of gravity, you give it slightly different conditions on the floor, and you sort of hope that when you actually physically instantiate this robot, the actual real parameters are kind of somewhere inside this manifold of all the random parameters you forced it to learn on. So if you make this thing too wide, you sort of give it an impossible problem. But if you start with system ID, you get a pretty good guess, you fuzz around that guess, you can really get a robot that actually does a pretty good job of training. And so you'll see here, all these little code snippets are from the actual Colab notebook. So you can go and you can ablate these things out and convince yourself that they matter. We go the other way for the students. We actually give them a bunch of zeros and they have to figure out what values to set these to get the thing to walk. And so what I want to show you here is this is actually a walking gait that was trained using the first two things. We got system identification working, we got a little domain randomization, and it's very cute. It's moving around, but there's a reason it's on hardwood, which just doesn't work on carpet. And it doesn't work on carpet because it just doesn't lift its feet up far enough. And it's basically overfit the simulator on a number of levels. It's learned that there are never bumps it's gonna trip over. It's learned that it can always rely on the surface friction of the floor. And we're like, okay, we need to do a little better. And this brings in the last trick, which is that you actually know a little bit about where the simulator is strong and where the simulator is weak. You even know a little bit a bias of like how you kind of want that robot to walk and feel. And you can do that. You can actually influence the training through the reward itself. You can actually set these parameters of don't push too hard off the floor, or don't shake your body too much, or try not to pitch and roll while you walk. And when you kind of bring all these things together, you can get a working gait that actually tries to balance being dynamically capable while being relatively stable and light. So this is the final gait. If you were to train one and actually put on the robot, it's very cute, it's very playful, it can have a lot of fun outside, but also if you do it on indoor environments, it can actually be relatively subtle and it can be relatively quiet. And so we were kind of proud to get a gait that was both less aggressive at low speed, but also more capable in terms of dynamic objects. And the Dr. Pupper team was so kind. They sent us some very early results of actually doing this gait in the hospital. And so this is, what this is showing is basically the anxiety self-reported by some patients over time. We have the pre-Pupper and the post-Pupper anxiety ratings. And obviously this is a small sample size and there's a lot more to do, but we were just insanely excited by this. And they were kind enough to share a really, really cute story, which is one of the kids, or Pupper accompanied them into the operating room, asked if Pupper could come into the bed before they finished their anesthesia. And I don't think we ever would have said that was safe with the heuristic controller. We did a lot of work on the neural controller. And so this is a picture of Pupper active with the patient, helping them as they actually finish the anesthesia process. I want to do a quick thank you to the incredible folks at Google DeepMind who actually brought this thing to life and helped us figure out our way through it all and kind of make this available both to students and enthusiasts. So that's a bit about how we get full body control. Let's talk about perception for a second. This is another area where if you as AI experts are absolutely ready to start like jumping straight in, perception's a more mature domain. It's not like there's a bunch of wild new architectures that are upending how we do perception. What is changing though is the availability of hardware and the speed of that hardware that we can actually put on a laptop cost robot. And so this is what our newest Pupper runs. It has an excellent, like this camera itself has very good light sensitivity, extremely wide field of view. We'll talk about what that matters in a second. And it has an onboard neural accelerator. I had to go look this up because I wasn't sure. I was like, this can't be true. This neural accelerator is actually comparable in power to a 2018 Tesla autopilot system, like a hardware 2. And it's just crazy to me that in less than half a decade, you can just put these super powerful systems on hobby level robotics. And what that lets you do is actually really, really impressive state-of-the-art closed loop reasoning. And so right now we run YOLO 8. It's actually a pretty advanced network. We can run that at 60 FPS with many different detections. And I want to show two really fun little projects that kind of brought to life. And I'll just show one right now. So this is so at the end of the quarter, the students do final projects. They always want to do one where they kind of do they'll usually do ball chasing or finding. This was one of the most impressive ones we've seen yet this last quarter. They were able to find, pick up, collect all the pickleballs in the scene and then bring them to the person who started them off in the first place. And I think it's just a testament to you're just standing on the shoulders of giants right now where you can run very high frame rate, you can do full in context learning, you can just set out and do really, really non-trivial things without necessarily collecting and labeling data. And so that just struck us. We were super excited by it. And then lastly, I want to talk about action planning. So this whole domain essentially, at some point you have to decide, okay, what am I asking this robot to do? How does it know what it's being asked to do? And how does it actually sequence those actions once it kind of figures out what it's being asked to do? Historically, we did have the ability to make the robot do cute things, but usually the process was the students would record some action, they would bind it to some button on the remote control, then when it was time to demo what they'd been building, they would basically set the robot down and press the X button. Now, obviously, the advancement in large language models has really changed how we do function calling on these robots. And so we started by building off of the work in one of the Deepmind papers. where it actually would generate Python on the fly. And then now, almost all of the modern LLMs directly offer function calling APIs. And so we can actually register the functions directly and call them. And it just allows for these very, very seamless interactions. So I'll just show, I love showing the student projects as a way to demo these, so I'll show off another one real quickly.
Pupper, wiggle.
He said wiggle.
Wiggle.
Pupper, track person.
Track person.
Pupper, stop.
Stop.
All right, so the latency is high enough there that we do still have an e-stop on the controller, but you can see that you can just tell Pupper what you want it to do, and you can get these really compelling interactions. The other thing that's starting to happen, though, is as we can actually really take advantage of in-context learning and prompting, it's actually empowered people who previously couldn't really do programming for Pupper to come in and actually start doing programming for Pupper. So the Dr. Pupper team has been in there being like, okay, I have opinions about how Pupper should respond. I have opinions about what actions Pupper should take. And so one of the requests they had was, could you give us some more like actions or physical motions? And so I wanted to end with a cute demo of some of Pupper's new capabilities. And what you'll see in here also is Pupper's ability to interpret a command, understand it's being asked to do two separate actions and sequence those actions, and that's something you just get for free with like great modern LLMs.
Hey Pupper, do you know any yoga moves?
Here comes that upward dog. Right away. Watch this. Upward dog, please.
That's pretty good. Can you show me maybe a downward dog and a Superman?
You got it. Let's roll right into a downward dog, followed by Superman pose. Here comes the double feature. Downward dog, Superman. Done. How do you like that? I'm always ready for more fun.
All right. Naturally, we're super excited to see what folks do with this. We're super excited to keep contributing to it. I hope at some level I've inspired you to think that like now is the right time as an AI expert to like actually give it a go and start playing with robots. If you need a concrete embodiment, we have one ready to go. I will end with QR codes on the screen. Obviously, first I have to say thank you to the incredible folks who worked on this. Again, Dr. Jay Tan and Professor Karen Liu, who's faculty at Stanford, who made the class come to life. Dr. Teresa Wen, who leads the Dr. Pupper program. Wen Hao and Ting Nan at Google Deepmind, who've been just incredibly gracious in their work on RL, and then all of the TAs and inventors, Nathan, Gabriel, Ankush, JC, and a special thank you to Lee Redden, who made some really thoughtful contributions, which have allowed us to actually start donating these to community colleges as well. And so with that, I will leave the QR codes on stage and answer a question or two, or give some time back, depending on what Razan needs from us right now.
Questions, we have time.
In the reinforcement learning, did you need to do something to make it walk in a way that's natural for dogs so it doesn't do something that, like, it's technically possible but looks unnatural?
Yeah, I anticipated this question. So it turns out when researchers first started doing this, it was so difficult, like the solution space is so broad that the dog would like learn to walk on its elbows or like put its head on the ground and shove off with one foot. And so the initial approach was actually to take that trajectory generator that we built, the old one, and then just attach a neural network to it. And so you can modify what the trajectory generator is doing, but you don't have to learn from scratch. This is actually work from Jay Tan at Google Deepmind. Since then, we have kind of learned just the right set of reward-shaping initial conditions. So we have a very heavy penalty for touching your elbows. We have a very heavy penalty for touching your nose. And like, if you just put all these penalties in place, Pupper actually does start to sort of do the only kinematically feasible thing left to it, which is like kind of walking sort of normally. But even there, you can get like, what if the elbows flip backward and stuff. So we sort of reward shape our way into that is the sort of long answer. But when we first kind of cracked this space, this was actually the original way that it was done, because it was just such a broad solution space. Since then, we've kind of figured out the recipe to get it to converge into something that we like.
Hi, Stuart. Thank you for your great talk. My name is Avid. I'm an electrical engineering student at Santa Clara, and I'm doing research in soft robotics with like an elephant trunk style continuum robot arm. And I'm thinking, do you see a future where we can really integrate a robot arm like I'm describing, like as a tail for Pupper in the same package with like rigid robots? Like, can we do that in a small package?
Yes, the question is, could we do soft robotics of some kind, like put a tail on Pupper or things like that? JC, Ankush, have you guys looked at this at all? I think the short answer is anything is possible, but I want to ask some of the experts and see if they've actually tried it yet.
There was one group, I think 2 quarters ago, who put an arm on Pupper, not necessarily soft.
Yeah, that's true. So I guess like the closest we've seen was a student project where they actually did put like a spot style arm on the back of Pupper, and it was very cute. It was able to like lift up candy bars.
Very neat. Thank you.
One last question.
Curious, hardware is always hard. There's like 2019 to 2022. I'm curious if you've done any ML for the designing and hardware iteration of making robots, so like the actuators and the actual design of things to effectively say like your reward function is cuteness, and then that intersects both the software and hardware portion of it.
No, we haven't done machine learning for that purpose. I think Nathan Cow is here. You can catch him in the back. That is the AI for cuteness, right over there. So you can catch him after this and talk to him about how are we doing that and what does that look like. And well, I just want to end by saying thank you, Rizal. It is such a gift to get to share this with folks, and thanks for bringing everyone together.
Oh, thank you. Thanks, Stuart.